Hello. Um, this presentation is the basis for mesh generation and mesh refinement using hydroBID flood. The content of the presentation includes the discussion of the layers that are considered for the mesh generation, the role of several of these layers including mesh density line, mesh density polygon, and a mesh break line that play a role in creating the mesh. Then we'll discuss the mesh generation process, the mechanism that considers GMSH for sizing the cells, and we'll see that GMSH is the program that we use to generate the mesh. Then we'll see how uh, um, we can generate the mesh only considering the domain outline layer without the other uh, modifier layers, followed by the use of the modifier layers to refine the mesh in different ways. Then we'll see the mesh ordering optimization, some issues when generating the mesh, and then finally uh, how to join break lines and component polylines in order to make the correct intersection of these lines. There's a lot of things to cover. This is very important presentation because as we have seen, the mesh is the basis for the model computation. What the model is seeing is not the terrain raster, it's nothing else that it's the basic data is all that is related to the mesh. So it is extremely important to understand how the meshing process occurs and how you can modify to adapt it to your project. So the layers that the model utilizes to create the mesh um, are essentially two groups. One is the domain outline group, the where you can have multiple polygons there, the mesh density line, mesh density polygon, and mesh break line, which are modifiers. And then we have the components. The components are based on also break lines, and they include break lines to define the alignment of bridges, weirs, dam bridges, or gates. Now, all of these meshes are used with a parameter that they have. All of them have a parameter that is the cell size. And the tri-mesh, which is the final result of creating or generating a mesh, it's a function of this cell size and a function of the alignment of the different lines and polygons that are in all of these layers. Now it may look a little complex, but as you will see, it's quite simple when you use it, and we will demonstrate that today. The first layer that is used, and it's the basic layer, as you have seen, you require having a domain outline layer, is the basic external polygon that defines the extent of the mesh. But also you can have internal polygons, as you see here, that define obstacles or islands within the mesh. It can represent a number of objects, not necessarily islands. It can be a building, it can be anything that would represent an obstacle to the flow. So in this internal polygons, there will be no mesh, so you have only mesh outside of these polygons. In between the internal polygons that you can have many of them, and the external polygon that you have a single one. Now each of these polygons have a cell size attribute. So that means that you can, for instance, select as we have seen in other presentations, we can have, let's say, a 50-meter cell size defined for the external polygon and a 25-meter defined for the internal polygon. And in that way, we can have a refinement around the internal polygons. It's not the case of this one because, as you can see, it's more or less uniform. Now, I want to point your attention to something that you can see here. If you look carefully, there are some areas here that have like a higher concentration of cells, like a smaller cells. You see it here, you see it here, 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 and here, and here, and here. And we'll come back to that, but bear in mind that there are several factors that affect the size of the cells, and cell size is only one of these factors, and we will come back to this. But bear in mind this high concentration or smaller cell areas that occur here. So we have the domain outline. We always need to have a domain outline. And then we have the modifier layers. And the first one is the mesh density line. It's the mesh density line is a layer where we draw polylines. And they are used to adjust the size of the mesh cells or elements based on the cell size attribute that you give to each of these lines. As you can see here in this example, you have these red lines are mesh density lines drawn. These are polylines inside the mesh density layer, and they have a cell size attribute. In this case, the cell size attribute for this one here on the left is smaller than in this one. So you see here that by having a smaller cell size, the mesh generator will create smaller cells on this along these lines than along this line here. So you can play with the cell size attribute of each polyline in the mesh density line layer to refine the mesh along the lines that you can draw. So these are very useful tools to improve or to have a higher resolution areas in areas that you want to have smaller cells. One of the main characteristics of these mesh density lines is that they do not force the mesh elements and nodes to snap to the lines. As you can see, the cell size can be different, but the elements essentially cross the lines. So these are not strong, what they call the strong lines. They are soft. They call sometimes soft lines, and the reason they are called density is because they are used to increase or decrease the density of the mesh around them or along their alignment. But this is very important characteristics that they do not force the mesh elements to align to it. So they are relatively flexible. That's also sometimes used in conjunction with the mesh density polygon. So in contrast with the mesh density lines that, as the name implies, are polylines, the mesh density polygon layer includes polygons, and the polygons also have the cell size attribute, and also they do not force the cell to conform or to snap to it. So the elements essentially cross the lines or the contour of the polygons that are drawn in the mesh density polygon layer. But what they do, in contrast with the mesh density line, that they will will force the generation of smaller cells, or cells that are on average equal to the cell size attribute that you give to it within the internal of that polygon. And then the program will gradually uh, change the size, as you can see here, from the one that you have assigned to the polygon, that in this case is much smaller than the one in the domain outline, toward the domain outline cell size. So you see why it's gradually increasing is because the cell size defined for the mesh uh, polygon is smaller than the one that it was defined for the domain outline. So this is something that is useful for river applications, because you can refine the mesh within the river and then let the floodplain has a less resolution. The other characteristic that these polygons have is that they can cross and they can overlap, and also they can cross the boundary or the domain outline. And when they cross, as you can see here, they force the mesh also along the domain outline to be on the size that you select for the polygon. So this is also useful because if you have this situation, and this is a river, you want the polygon to also force the mesh size to be altered in the domain outline, and not let only the domain outline be of that larger size. So we will make use of that too. This tool is very applied in many projects. So the third modifier layer that we're going to be using is the mesh breakline layer. And the mesh breakline layer includes polylines as well, in the same way that the mesh density layer included polylines. The mesh breakline also include polylines, but in this case it forces the mesh to conform to the line. You remember that the mesh density had cells crossing the line. In this case, you can force the mesh to pass through the along the break line. They also have a cell size attribute, so you can also use it to refine the mesh, while in addition to refining the mesh, you also force the mesh to pass through it. So this is a very important characteristics. Of course, the mesh break lines have to be used with care, because since they force sometimes too much the mesh, they can create some issues, as we will see later in the presentation. Now, just to make a comparison so that you understand well the differences, on the left we have the mesh density lines, and on the right we have the mesh break line. And you can see here that in this case they follow the same alignment, but the effect they have on the mesh is quite different, because in this case the mesh density line do not force the elements to go along or snap to it, while in this case it forces. So this is useful if you have in your project area walls or structures that are and you want to make sure that the mesh captures correctly maybe the extremes of the canal, the walls that form a concrete canal or something like that. While these are used when you don't need so much detail in the mesh to conform into these lines. So we can make use of both simultaneously, and we will see when and why. So in addition to the three modifier layers, we have the the structures, the hydraulic structures, bridges, weirs, dam bridge, and gates. All of these components are formed by break lines. So if you want to define, let's say, a bridge that go through here, you use the bridge component and you draw a line or a polyline, and that polyline works in the exact same way as the break line to the mesh. They do have a cell size attribute, and they force the mesh to snap to it. So this is something that can be used also in conjunction with the other modifier layers. So we will see in each of the presentations that we have for each of these components how they work and how you can use together with the other mesh generation modifiers. Something important to keep in mind is that whenever you create either a mesh break line or any of the polylines that define either bridges, weirs, dam bridges, or gates, you need to regenerate the mesh, because since they modify the mesh alignment, it is important to ensure that the structure that you define along this line has cells at each side and they are not overlapping the line. That is very important, because otherwise the formulation that is used to account for the effect of bridges, weirs, dam bridges, and gates will not work properly in the model. Now, I will give you a more or less detailed description of the processes and the method that we use in the mesh generation program. It is not something that you necessarily need to think about every time that you generate the mesh, because as we will see, when you create a mesh, there is the program does it very quickly, and I want to give you, before getting into these details, a simple demonstration of the different things that we have learned before entering the details. I have here a project that is the same project that we use for the first example, and as you can see here, we don't have in this project any of the layers that we use as modifiers, and I will go ahead and create, using the new template layer, I will use the mesh tab here and create a mesh density line layer, a mesh break line layer, and a mesh density polygon layer. And I will show you quickly how to generate the mesh with these options. So if you turn off these layers, and you see for the domain outline we have a 20-meter resolution defined for the cell size. So the cell size for the domain outline is 20 meters. If I try to generate the mesh only with the domain outline, what happens is that we get a more or less uniform cell size distribution, as you can see here. Now, if we want to use the mesh density line, as we saw, I will click on activate the mesh density line, create a polyline by putting in edit mode, adding a polyline, and see that the mesh density line can be and extend beyond the mesh. It doesn't matter. I right click, I enter a value. I will enter a value here, let's say of, let me put a 10 meter, so half the size of the domain outline cell size, and I will save and I will regenerate the mesh. So let's see what is the effect of the mesh density line only, together of course with the domain outline, because the domain outline is always present here. So you see that along the mesh density line, let me put it up here so that you see the alignment, we have smaller cells. So we have a higher resolution, what we call a high resolution mesh along this line. And if we zoom in, we can confirm that the line does not affect, other than the size of the cell, it does not affect the alignment. So it goes along. There are cells on one side, in the other side, but it doesn't affect the alignment of the mesh. So let me now create a similar polyline, but using the break line. So I will put this in edit mode. Now I will not cross the boundary. I will tell you why later. There are issues if you intersect the other hard lines that you have in the project. If you intersect, that may create some issues, so unless you do it in the right way. So before that, I will just create a break line that goes in a similar path as the other one, but will not cross the domain outline polygon. It stays inside and do not intersect it. Again, the mesh break line also has the attribute, which is, in this case, I will use also 10 for cell size, and I will save and I will create the mesh. So I want to show you the differences, and as you can see, the process is normally very fast of creation. Now you note as well that there is a another refinement along the line, but in this case, let me put the mesh break line on top of the other. You see that the mesh is aligned along the break line. So that's the main difference. But this is very useful, because if you want to adapt your mesh to some structures, the break lines are very useful way to do that. And again, the last thing I wanted to show you is that the mesh density polygon is another tool that, in this case, you create a polygon. I am creating a polygon along, as we did in the other example. Let me put it here, 10, edit mode, and then refine. So this is not a very good drawn polygon. I just wanted to show you the effect of it, and it's doing all the optimizations, mesh generation, and so forth. And look that now the mesh is very much refined within the polygon, and then the elements gradually increase up to the domain outline side. Now you remember that I told you about these areas of fire concentration points. Well, in addition to all of the factors that I have mentioned, there is another one, that is the number of vertices that are in the polylines or in the domain outline. So every vertex or node that you draw in your domain outline or in your break line will be forced to have one node. So you see here there is a node here, and that creates necessarily a node of one element there. If we go to a next one here, you see another one here. So if you would have created many nodes here along this polyline, then that would have forced the creation of nodes there. So that it's another way to densify the mesh, is by adding vertices to the line. So if you would have created a line that has a very small distance between the nodes, then you would have had a lot of resolution here, and that is what happened in the previous plot that I showed you here, that in these points you may have some more vertices that you may have in other areas, and that's why you have these clusters of cells that are more concentrated in along these lines. Okay, so that's the as you can see, it's very easy to generate a mesh and refine it. It's a process that you can use very rapidly until you get the mesh that you need. But having said that, it's very important to understand how the mesh generation works, because sometimes that will help you to have better meshes, and if you have better meshes you will get better results. Now we have seen we have the mesh generation based on this the information that you have on the layers, domain outline, mesh density line, mesh density polygon, mesh break line, and the structures. Using that information, the hydroBID flood plugin creates a .geo file. That geo file is the native format for data in the GMSH program. GMSH is a open source program for mesh generation that it can generate very complex meshes, including 3D meshes, but we use only the two-dimensional component of it. But based on the information on the geo file that hydroBID flood creates from the data that you enter in these layers, the program is executed and will create a MSH file and eventually the tri-mesh in the QGIS system. So this is the general steps that are followed in the mesh generation program. Now the size of the cells, as we have seen, depends on a number of factors. The cell size for each of the objects are in the layers, the spacing between nodes, as I mentioned previously, and also something that occurs in the background and is not very clear because you don't see it directly, is the interpolated raster from the cell size. So based on this information, the plugin will create a raster, but in this case it's not a raster of elevations, it's a raster of cell sizes that the GMSH program uses to create the mesh and size the cells. So when using only the domain outline layer, the only factors that are used, or the only parameters that are used, is the cell size of the domain outline polygons and the spacing between nodes. There are no refinement, there is no other there's no creation of raster layer or anything else. Now in that case we have a densification routine. So let's say you start with a domain outline that is like this, and the cell size that you define is smaller than the distance between the vertices here. So we use a densification routine that, based on the cell size, will create an intermediate layer that is the domain outline under bar D, and in turn that will create the geo and then the rest of the process is the same. So this is very simple process that occurs when the cell size that you request is smaller than the node spacing. Okay, that's very important to keep in mind, because if that would not be the case, if you would have a node spacing that would be smaller than this cell size, then the node spacing will be the one that will control the size of the cell. Now, when you use the modifier layers, the process is different, because we first need to know the data that is contained in all the modifier layers and in the structure, hydraulic structure layers. We use the densification routine based on the cell size, and then that we need to create also for each of these layers some information that will tell the generation program how to refine the mesh depending on what data is contained on these layers. And with this information, then we use the interpolator to create this raster. So we have the original domain outline with maybe break lines or density lines. We densify the domain outline and the density line. We make a triangulation, and then we make an interpolation so that we generate a raster. Now this raster is not, as I mentioned, a raster of elevations. It's a raster of cell sizes. That means that on the dark areas here indicate areas of very small cells that proportional to what you have here, and in the lighter areas indicates areas where the cell size requested is not as small as in the dark areas. So this raster is used by the GMesh program to generate the mesh. So when generating the mesh with these modifier layers, the raster is written to a file that is the TriMesh LCASC, which is an ASCII file. It's an ASCII grid file, and that in turn is converted into a TriMesh layer that can be read by the GMesh program, and that is what creates the final mesh. So this is what happened. This is a map of a raster. It's a TriMesh LC raster. The colors again indicate the size of the cells. That means the green are 15 meter size, more or less, in here, and in the darker brown will be 2.5. So you have higher resolution in the brownish areas and less resolution, larger cells in the greener areas. When you see the final mesh, you see something like this. So you see a lot of cells along these lines or in the main channel. As you can see here in the brown, these are cells that are on average between 2.5 and 5 meters along these lines, these areas. And then in this area here, you see much larger cells that are in the order of 12 to 15 meters. So in this way, the advantage of having that, and again, you don't see that directly, something that you need to be aware of, but it's not something that will, you don't have control directly over that except by modifying the layers. But this is something that occurs in the background and helps to have a gradual change in the cell size from a high resolution area to a low resolution area, as you see here. So this is something that I just wanted to give to you. It's a general information, but it's useful to have it in the background. Now, when the program creates the mesh, it assigns a unique number to the nodes and a unique number to the cell. So every cell has a number, and this number will be used by the model to compute the results of that cell. But you need also the connectivity, so you need to know one cell, what are the neighboring cells, because that is important for the model to exchange um, water from one cell to the other. That's the way the model works, by combining the cells together. So the problem is that by default the mesh generation program creates a random numbering. That means that you may have one cell that is cell number 5 besides a neighboring cell that is cell number 360 or 400,000. So they may be very far apart in numbers. What is the problem with that? Well, the problem is that when using parallelization technique to compute the results, as the hydroBID flood does with GPU or with the cores of the computer, the CPU, it is important to have the cells that are close together to have a close numbering as well. So it's good to have, let's say, cell 5 close to cell, maybe the neighboring cells should be maybe 10 or 15 or that order, but not 400,000, because they would be, when they are organized in multiple cores, they will be very far apart from each other. And that distance, even though you may think is not important, it creates a lot of overhead in communicating one core with the other to exchange the information that is necessary to exchange between one cell and the others. Now, to avoid that, we created an option that is the optimized mesh cell ordering here, that is accessible in the configuration tool of the hydroBID flood tool icon, and that is now set by default a check, but I would suggest you can go every time you are going to check your mesh or refine the mesh, especially the meshes that you would use for production runs. Check that this option is selected, so that the numbering of the cells is optimized for faster computation. This is important because in our test we have found that there may be accelerations of up to 30% just by using this option. So there is nothing to lose essentially here. Now, some issues that can occur when you have really big meshes. Now, I have said before this, and I really recommend this process. Do not generate a very high resolution mesh, a mesh with a large number of cells initially. When you are developing and doing a project, start simple. Start with the smaller cells, with the smaller meshes. That means big cells, or relatively big. Even if they are too big for your case, doesn't matter. You just use it to set up your whole project. That will help the model run fast. And once you have everything put together and you know that it's combining well, then you go ahead and refine the mesh to the resolution that you really need. And that resolution sometimes is it's a huge resolution. It may lead to millions of cells, and that can create some problems for QGIS, and also can generate a problem for GMesh program. So if you're having a mesh of many millions, say 7, 10 million, 12 million cells, you may run into problems, because that can lead to a raster file, the raster file that I talked before, that can be on the range of 10 gigabytes of larger. If that happens, then GMesh will have a problem with that, and will not be able to do it. So you would need to try to be on a range of cells, of number of cells that are less than maybe 10 million, or maybe 8 million. But in many instances, in many projects, you don't need to go beyond a few 100,000. So we are talking about really big meshes here. Um, just so you have an idea, we have worked with people doing very large projects in Australia, that they have been modeling the complete island of Tasmania, that has more than 300 watersheds, with a single mesh. It's a mesh of 12 million cells, and it works, but you have to be very careful in how you organize your data, and how you refine the mesh in order to avoid these limitations. Many projects, you are well below 1 million, and you will never probably encounter this limitation in your practical applications. Um, so if you encounter that, in any case, you have a factor that you can use to try to resolve that issue. And this is also in the tools menu, you have the hydroBID flood setting, and you have this resolution factor here that is by default set to 1. So if you increase it, that will help you to decrease the size of the raster layer, and in that case, that will help in reducing from maybe 10 gigabytes to 5 or so. So if you multiply this by 2 or by 3, then you probably will solve the problem of that issue. So it's an internal parameter, but you can have control to work with that if you encounter that issue. Another problem that often occurs is when you are creating a mesh with a lot of restrictions, or when you have a big changes in the size of the cells. You are varying the size of the cells too much in a short distance. You may run with an issue of angles that are too acute. You have acute angles, less angles of the cells of less than 5 degrees. And the model doesn't like those cells at all. The model likes cells that are close to equilateral triangles, or even these triangles work well. But if you have triangles that are extremely elongated, as this one here, that will lead to problems in the model. As a matter of fact, the model does not let you have cells that have internal angle of less than 5 degrees at all. And for that, there is a tool that is allow you to create a list of what we call illegal cells, and then you can select them and directly use zoom to cell and see where the areas are where you have these cells, and then you can go ahead and correct what the causes that generated those cells. So it's very simple tool to use, but it's also good to analyze or to check if you have these cells in your mesh. Anyway, you will get a message, but this tools is there for you to use. So how you access that? In the tools menu, you have the command check internal angles of tri-mesh cells, and when you do that, there will be an automatic process that will check, and it will give you the list if there is any illegal cell. Otherwise, it will tell you that you are good to go. But if you get the list, then you can zoom to the cells that have that issue. Okay. Another issue that can occur is when you are using a domain outline polygon that comes from rastering from vectorizing a raster line. So you may have, let's say this is a contour line that you want to use, or this is the boundary of a watershed, and then you convert that into a vector and then you copy to the domain outline. But when doing that, since the raster is formed by pixels, you may get a vector, but the vector is like a staircase, like you see here. And the problem with this is that there will be one node at each of these breaks in the polyline. And as I indicated before, each vertex or node in the domain outline polygon, or any of the lines in break lines as well, will force to have one node. That means that you will have tiny cells along all the boundary. And if you have that, the cell size that you select will have no effect at all, because the mesh size will be totally controlled by this size. So you have to be careful when vectorizing rasters for generating the polylines, because they can lead to these issues there. Now, how do you solve that problem? Well, there is a tool, as there are many in QGIS, that is called Simplify. So it's in the vector menu, geometry tools, Simplify. You select the what it does is remove nodes from and redefines the domain outline or the polygon. So it removes nodes by having a larger distance between the vertices, and that larger distance is defined by this tolerance here. So you may play with that in order to simplify and remove the, that high density points, and that will help you a lot in improving that external polygon. Now, you recall that I mentioned before that you should not intersect the mesh break line with the external polygon. And what I meant is that you should not do that in the direct way that you would do it, because what happens is that when you make an intersection of the two polylines, that will create a vertex, and that vertex may be very, very close to another vertex on the line, and that can create a lot of problems for the mesh generation program. So the way to do it is to ensure that the intersection occurs at a vertex of the intersected line, so that you don't have to ensure that you don't have two vertices that are too close together. So that's the right way to do it, or the correct way to do it. Now, how do you do that? How do you ensure that when you are intersecting a line, that line will intersect at the exact node that will not create a problem? Well, for that, we need to use another tool that is available in the QGIS system, that is called the snapping toolbar, or the snapping tool. The snapping toolbar will help you ensure that the intersection occurs at a node or a vertex, and that will solve the problem that I mentioned before, that will allow you to intersect polylines and break lines and domain outline polygons without the issue in the mesh. Now, sometimes the snapping toolbars is not selected by default, so you have to go to the toolbar menu and select the snapping toolbar by selecting it here, and that will create a toolbar with a number of tools. Has several icons and boxes and drop down menus, as you can see here. The first time you use it, you need to configure it, and we'll see how to use it. But essentially you have the activation tool, or this icon over here, and this is an icon that you will need to click in order to activate. It will make your nodes come together to snap to the line, so that they will snap to the correct location of the nodes. Then you have the selection option that it will work either in all layers or in specific layers. The way to work with the with the snapping toolbar, in this case we recommend using the vertex option, because that is what will allow you to draw the line crossing through vertices. The distance that the tool will use to snap to it. So for instance, if you put 5 feet here, or if it's meter your units, when you move the cursor closer to 5 feet, then it will snap to the node on the intersected line. So there are other options here that you may use, but these are the principal ones. So when you're using this tool, what you do is, when you are drawing the let's say a break line, and you have the domain polygon over here, when you get closer to the line, or very close to the line, you will see that the node on the other line, or the intersected line, will be highlighted, as you can see here. And you get close to it, you just click, and then what we'll do is to pass exactly this line and join it to this point, so that you can continue extending the line outside if necessary for the intersection. So it's very simple to use, but if you don't use it, then you will not ensure that the intersection occurs at the nodes. The other thing that is also important is when joining polylines in the components. I'm showing here an example of a weir and two weirs and a gate. And in this case, when you're using the model, you need to ensure that they align in the same nodes, and they join in only one vertex, so they don't give a gap. Because in this case, there is a gap in between this weir and this gate, and there may be a gap here. And then when the mesh generation program is doing the mesh, you will see that there is something very wrong on this location, where you have so close together nodes here. There will be even illegal elements for sure in these locations. So what you need to do is to join the lines in such a way that the ending vertex of the weir is the first vertex of the gate, and the same way it happens in here. And this is done exactly with the snapping toolbar. So what you will do when you're creating the weir, you create first let's say one weir, and you're creating this gate. Then you use the snapping tool, and when you get close to this intersection, the program will snap to it, and then you click, and the intersection will be in the same at every point where you want to join two break lines. Now, important points to remember from what we have seen today. The mesh density lines can cross domain outline polygons or other lines and structures. There is no restriction. There is no problem created, because the mesh density lines do not force the mesh to conform to them. The mesh density polygons can also overlap. Domain outline polygons can extend outside the domain outline, and they can overlap, they can intersect. They have no issues whatsoever in that regard. However, it is recommended not to intersect break lines with other lines, including domain outline, polygons, break lines, or bridges, weirs, and dam bridge gates, unless you use the intersection in the correct way using the snapping tool so that the intersection passes through nodes or vertices of each of the intersected lines. So these are important points to remember. Well, that concludes the presentation, and you are welcome to make any question.